Hi guys and welcome to yet another Genome2D Devcast. Today we are going to talk about particles. Everybody loves particles. So that's one of the reasons I decided to refactor the particle system inside Genome2D. I will kind of improvise here. The refactor is still not 100% finished. It's working, but there may be some small API changes and optimizations here and there. So let's start with the old stuff. Some of you have huge projects built on Genome2D and a kind of like questioning if they should move to the particle system, the new particle system. That's why, like I did a few times in the past, I moved the old stuff into the deprecated package. So you will find it in the com.genome2d com deprecated package. And all the classes have a D suffix. So if you want to keep the particle system, keep using the old particle system, you are free to do so. And I know that if there are huge projects and you still want the new engine, or the new version of the framework due to the bug fixes or small feature requests you send me. That's why I keep the old stuff there. But outside of small tweaks or small fixes, if there are any bugs or if you report any bugs of the old particle system, I will no longer support the old particle system with any major features and stuff like that. And you should move to the new one. And as you will see in this video, the new one is absolutely amazing, and it combines the multiple stuff from the old ones and even some new stuff. There were two particle systems in the old particle system. There was the G simple particle system and G particle system. The difference was that the G simple particle system wasn't extensible. It was just the rigid class with some kind of specified properties that were settable. So you could like set the start red color to the end red color and velocity and stuff like that. And the particle system iterated on these properties, and they were interpolated or in a rigid way, so you could create the most common particle systems using this. Then there was the G particle system, which basically didn't do anything out of the box, but it had the EG effector and EG initializer. These were two interfaces where you could add any number of effectors and any number of initializers into the particle system, and effector was affecting the particles during the update step, and initializer was giving the particle the initializing or initialized the properties of the particle during the spawn. They are no longer there in the new particle system. And as you know, the old particle systems were components. So if you worked on the Genome2D context, you couldn't render the old particle system or couldn't use it. You could create a node and add the component there, and then in the post render in the Genome2D, you could call the render on the node and render the particles in that way. But it was a limitation, so I wanted to decouple the components part from the low level part. So the new G particle system is not a component, is a class that can be used to render without any node, any component, so you can render particle system on the canvas without using nodes at all. There will be a component, there is not yet, that will wrap the G particle system, so it will call the update on the G particle system, it will call the render of the G particle system, and it will invalidate the position of the particle system to the actual node position or transformation. Very simple class with a few lines of code, but you can use the particle system without that. Additional limitation in the old particle systems were that each particle system was basically an emitter. So if you, for example, had a slightly complex particle system, like you wanted a fire, which a fire is emitting some kind of fire particles, then it's emitting some kind of clouds or dust particles, and then it emits a little bit of sparks here and there, for example. So these would be three different particle systems in the old system. So you would either have you would need three nodes with three nodes with each with a particle system attached, and move them there in some kind of hierarchy. So you had a wrapper node that would have all these nodes with these particle systems. Now particle system is not an emitter. Emitter is decoupled from particle system, and each particle system can have any number of emitters. Then there are modules. Modules are basically effectors initializers in one. So each emitter can have any number of modules, and each module can be specified to be an update module or spawn module. Spawn module calls spawn function on each particle, and update module calls update function on each particle during the update step. Spawn is called during the particle spawning, and update is called during the update step. The module can be both spawn and update as well. So let's start with a simple example. I created this wrapper. There is a super class here that has all the unnecessary info. There are like Genome2D initialization, the loading of assets. I didn't want it here, so it's more clean. That's why I put it in the superclass. So what we do, we initialize the genome and load some kind of textures so we can render them, obviously, but we are not going to talk about that here. And after all this is done, we call the init example, and here we create a G particle system instance. That's our particle system where we will add emitters as we need them. Most of the time you will probably need a single particle system, and all the emitters have, for example, you can have even a global particle system if you want to for some reason, and then you can have an emitters on nodes that will move inside a particle system. Now we need some kind of emitter. I will unmark this one. It's better for our first example. As you can see, the emitter has some kind of position inside the particle system. Particle system can have a position as well if you want to move the whole particle system as well. And each emitter can have a relative position inside the particle system to the particle system origin. So this emitter will be at 400 and 300. Since our particle system doesn't have a position specified, it will be at the 0, 0. And our canvas for this example is 800, 600. So this emitter will be in the middle of our canvas. Then we will set a texture on emitter. I thought about this for quite a while, if I should put this property there. But most of the time you want for a single emitter to emit particles with a single specific texture. You can do this in some kind of spawn module. During spawning you can assign this texture to the particles. You can still do that. But to simplify this, I added this property to the emitter itself. So if a particle is spawned, it will automatically get the texture of the emitter. You can even set null here if you want to. Automatically it will be set to this emitter. And then there are the spawn modules I talked about, and you can assign a different texture there. You can animate it if you want to. Then there is a rate. As in the old G particle system, not the simple particle system, we have a curved rate. So you can specify any curve. It can be Bezier, it can be linear, it can be both. And the particle system will, or the curve actually, if you call an interpolate on it, will return an amount of, or the actual rate at that time. So if you know how curves work, particles in Unreal Engine, or I think even in Unity, you may know. So this is how the rate of the particle system develops in time. So this will emit 100 particles. This is a constant curve. You can create any curve there if you want to, like some kind of, it intensifies during time and then falls off. And I'm not going into explaining into these curves. If you want to, you can write me an email or shoot me on a forum, and I can delve into the curves. After all, it's open source. You can check how curves work, and if there is interest, I can do a devcast about this. So this will tell that the emitter has a constant rate of 100 particles per second, and the emitter duration, or not per second, per the emitter duration, obviously, and the duration is 1 second. So after the duration ends, the particle would stop emitting, but we set it to loop. So this will basically emit 100 particles per second and then go again, 100 per second. And now that's the funny stuff. We need a module. Otherwise, the particles wouldn't do anything. It would just spawn a particle, and the particle would be there indefinitely at the position of the emitter. So we add a simple emitter, simple module, and this one is called velocity module. What it does, as you can see, it's both spawn and update module. So during spawning, all particle will get this function called on them with the emitter and particle instance, and it will add a simple velocity in a 2 times mat_p, so in a whole radius, and a random scale, and it will set the particle total energy to 2000. And during update phase, each particle will get this function called on them with the emitter particle and the delta time of the actual update step. So we will update the position of the particle with the velocity times the delta times, because we want it to be frame independent, and it will accumulate the delta time as energy, so we know how old basically the particle is. Then set an alpha to the inverse of the accumulated energy. So basically this will fade out the particle based on its lifespan. And if the accumulated energy is larger than the total energy of the particle, we will tell the particle to die. You can't call dispose on this particle because it may get screwed up, but sometimes, for example, if there are multiple modules, they will get executed in the order you added them. If there are multiple modules, some modules can actually revive a particle. I had such modules, for example, during collision, that it actually died, but other module was doing a collision. You know, the sparks, they lit up more if they collide. So it revived the particle, put some energy into it, and so it may die during this update module, but it may be revived during the next update module. So, and after all the update modules are called and a particle has to die, the particles or the emitter will iterate all the particles and dispose those that should die. Never call a dispose directly. You will not save anything because the iteration of the particles that should die will be there anyway. So let's compile this. And this is our particle system. As you can see, I'm using WebGL to run the examples. Some of you are asking why I'm using a switch to WebGL instead of Flash. Don't worry, I still focus on Flash, and most of the features are Flash only. Or not most now, but a lot of the features are Flash only. But if I post a demo and a lot of people just click it on Twitter or something on their mobiles, the Flash doesn't work obviously on mobile. So I decided if it's possible for the feature, I will build the demo as a WebGL example. So all the people that click the tweets or something will automatically see it, because it works on iOS and Android. It works everywhere in browser, and it works actually quite fast. So this is our simple emitter. I have this feature in the superclass that the emitter should move to the mouse position if I click it. So as you can see, this is defaultly set to use world space. So the particles are once they are emitted from the emitter, they will have their own coordinate system. You can basically set it to use local space, and then they will move with the particle system. It's still possible. Just set the use world space to false in the emitter. So let's show you something different. What I have here is a new type of module. That's basically the only type of module that is now available inside the actual Genome2D Genome2D source code. I will add more modules if I see fit, but most of you will just create your own modules. They're really simple. What I have here is a script module, and this is something really special, and it's just something that I will implement in multiple areas inside Genome2D, not just particles. And that's the possibility to script something, to run scripts during runtime and compile stuff during runtime to edit. So let's compile it and just check it out. Okay, as you can see, it's running a script module, which is a specific module that compiles this script during runtime and runs it on the emitter as a module. So as you can, this is a hex language. This is a hex script, but this is not compiled during our compilation time. This is compiled at runtime using a hex script library, which is available in hex, and with some limitations, but you can use pretty much anything hex offers there. And what this script module does, it compiles the script. You tell it should compile, and it checks if there is a function spawn defined. If there is, it will be automatically an spawn module, and if there is function update defined inside the script, it will be update module as well, and it will call these two functions during the spawn and update accordingly. So if we just change this, we can affect it during and compile it during runtime. So we want, let's say we want some kind of fire. So green to half and particle blue to 0. And compile it. As you can see, we now have orange particles. We didn't recompile the Genome2D, we didn't recompile anything. The example, this was compiled inside the JavaScript we are running. And since we want a fire, we want a blend mode as well. Set it to 2. And we have a nice fire. So this is a really powerful feature, the scripting. And currently it's inside Genome2D. It's compiled. The hex script libraries compile into Genome2D, but it's used just by the particles. But you can use it pretty much to anything. And I will probably add more features into Genome2D that utilize it. And what I did, I am working on macros as well, that you can actually do this in some kind of editor and then tell Genome2D that it should compile the script as a part of the source code. You can include it using macro. There are some limitations, but I'm working them off. So what we are going to do next, most of you saw my examples or demos with fluids. That's what started me on this whole of particle refactoring stuff. When I did research into the smooth particle hydrodynamics, I did it outside of Genome2D. I did all this outside of genome particles. I just used Genome2D to render it because I iterate quite fast during various calculations. My ideas. I didn't want to mess the Genome2D source code. Now that I am quite happy how the fluids turned out, I'm implementing inside the particle system, and you can use them as well. So what we do here is that we need to tell the particle system where it is or its area for the fluids to work, because fluids work with spatial grid partitioning. I used KD trees, I used binary trees, I used Rankata, I used quad trees with Rankata, and believe me, spatial grid partitioning is the best way to go with the language limitations as well, and not really language limitations, but how some stuff is called, or how fast it is inside Flash and JavaScript. Anyway, so it will tell that this particle system is in this area, and it should break it into grid cells of the size 20. So it will break the area into these grid cells, and then during each update, it will go over all the particles and assign a cell. So each cell have reference to all the particles that are inside that specific cell. Then there is a next step is that we need a neighbor lookup, because if we want to do any kind of collision or interaction for fluids, we need to know which particles are inside a radius around another particle. So if we want to calculate this, that's why we do this spatial grid partitioning. And now we just need to look all the particles inside the cell the particle is and all the neighboring cells, and just check the radius, check for those. We don't need to do the brute force each with each. So basically n times n. So which would be really slow. Now we are in logarithmic time. And we tell this particle system that it should enable the smooth particle hydrodynamics for it. So this tells it that how it should manage the grid, but this flag tells it that it should do the pre-calculation, so the grid calculation, then the neighbor lookup, and finally it should calculate the forces for smooth particle hydrodynamics. So basically it will call calculate the forces on all the neighbors it found, so all the particle pairs. So what we also need is to specify for the emitter that it should enable smooth particle hydrodynamics, because we can have a particle system with an emitter that emits fluids and with a different emitter that doesn't want to emit fluids, so it will not interact with fluidy particles. It will basically just emit particles like we did in this example before. So it will be discarded from all the neighbor lookup or the force calculation and stuff like that. Only emitters marked that it should have the smooth particle hydrodynamics enabled will be calculated inside this step. So let's just compile it. And what we forgot to do is that we need a special module for the forces, because now we have all the fluid forces, density, pressures calculated, everything, but the particles don't react to it. They are not updated according to those forces. So we have a special module that I will add to the Genome2D source code. I can even show you. It's a very simple module. It will basically work with because these are the density, the fluidics, and some quite a few more fluid properties for the particle. So these are calculated during the smooth particle hydrodynamics step inside the particle system. And if you don't use them, the particles will just behave like they normally do. So what this does is just apply these forces to the particle velocity, which we then use in our other, here for example, our other modules. If we just had this module, it will not do anything, because as you can see, the particle position is not updated according to the velocity. And always use the SPH module as first one, because if you do something with velocity somewhere else, and so this will basically update your velocities with the fresh info from the particle system calculations, and then you can do anything on with the other modules. But try to use, unless you know what you are doing, try always to have the first module, the smooth particle hydrodynamics module. So let's recompile. Okay, let's check it. We probably forgot something. Oh, we have an error. We didn't recompile. So now we recompiled. And as you can see, now we are emitting fluids. I will just change the scale to something more feasible. And now we are emitting fluid particles. We don't have the collision lag in the demos. We can add it there, no problem, but we don't really want it. We can add it some kind of gravity. Why? This will be probably too much. Oh, not. So we can have a check with the. Okay, I can probably here. I can just add this to the. That's from the demo to this script. No problem. And we will just 595 595. And now we have a bottom collision like you see it in the demo. We set the total energy to 12 seconds. We will have a lot of particles and they will live longer. As you can see, fluids now work right away. So another thing we want, what I created here, is a special emitter. It's not really a special, it's a basic emitter, but as you can see, it doesn't have any duration and any rate. What I do here is I call burst on this in a way I want. I will show you. So let me disable, for example, this. So it has no, we see only this one emitter. It has no rate, no burst, nothing. I call burst on it manually, and what I do is basically on mouse down I generate the particles. So I burst them here, and this is the script for it. I'm not going into details of the actual grid I used to draw these particles, but you can basically, what I wanted to say is you can manually add particles to the particle system, but with the burst method. You don't really need to calculate the rate if you don't want to, or stuff like that. So what I can do this here, you wouldn't do this here, but you would do it in the code probably. But I can. It's a simple Boolean. I can enable the smooth particle hydrodynamics I disabled before. So let's check it out. Oh, why did it didn't recompile? It should recompile. It works. Let me check back here. Okay, it did recompile, but we didn't call the actual function because we didn't spawn any new particles. So if I do, no, I wanted to have it like this. So we have this special emitter. We burst a few particles into the particle system, and we can change it using this. And what I did here is that I will set the emitter to enable the smooth particle hydrodynamics to true. It compiles, but this doesn't run automatically because it runs only on the particles being spawned. We didn't spawn anything, so we spawned some new particles, and as you can see now the particle system is part of the simulation. Why it doesn't move though? Because the particles are fixed. This is a special parameter for the fluid particles that will tell the particles that they should calculate the forces with other particles, but they shouldn't calculate forces from themselves, and they shouldn't move. So their force is actually zero, and therefore their velocity is zero. So they are just the barrier for fluid particles, but collide with them. We can do a little bit more time with the particles in the other particle system, so we will fill the tank a bit more. It's kind of nice. This is just some fancy stuff. I will just create the standard scale 1 particles. What we can do though, we can make these particles not fixed. As you can see, it's here in the update, but this update is not called because it's called update to, and the script module checks if there is a function called update defined in the script, so this function is not called. If I compile it like this, this will be a valid update function, and these particles will be then called with this function, so therefore they should make be not fixed anymore. So let's just check it out. And as you can see, our fixed particles are now standard fluid. And now if we create them, it's just the fluid particle. Very nice. As I said, this Genome2D Devcast is quite long, but let me show you something a bit more final stuff, I promise. So what will we do here? We will just not do any SPH, and we will add a new module here, and it's called emitter spawn module. It's a simple module I just created, and as you can see, what this module does, it creates emitters for each spawned particle. Yes, you are right. One of the demos I posted was particles emitting particles, and this is one of the ways how to do that. You can do that other way. You can extend the gParticle instance, if gParticle class, and it's possible that way as well. I can show it in a different tutorial, but this is how to do it using modules. So we will create a map for the emitter instance to assign the emitter instance into the actual particle, and if the particle dies, we will turn off the emitter. So we are basically reusing the emitters as well. We're not creating the new ones unless the particle is a new particle. It's not a pooled particle, because as you know, all particles are pooled for all the particle systems, all the emitters in the Genome2D, unless you specify that this particle system or this particle emitter should use a custom pool. Other than that, all particles are pooled in all emitters. So these particles that die will just be reassigned as a new spawned particles, and therefore the emitters will be reused as well. So let's check it out. Compile it. So now we have particles emitting particles. Let's just make it a little bit ratey. So again, you would do this somewhere. Oh, we can't rate it right there. So we will, because we would need to tell the script that there is some kind of G-curve class. That's a hex script specific stuff I'm not going into. So let's just say we want 5 particles. So we will see how they emit the other particles. And let's just make this velocity module a little bit slower. Okay, and now you can see particles emitting particles with a trail. And now we can combine it to have fun as well. What we can do, yes, you called it, we can actually tell this emitter to use the SPH module as well, and so what we have now, we compile it, we have particles emitting fluid. You're right. Nothing beats that. We can now. Oh my god. I didn't want that. I will just add this back to show you that it's really fluid. So what we can do here, we have particles emitting fluid, and now we add barriers that the fluid will interact with. We can do anything with this system, and if you have any stuff, okay, we can. Sorry that it takes so long, but I just wanted to add something. We will add to this velocity module. We will add a little bit more gravity, just for fun, and we will add the check at the bottom, the collision check. I'm just having fun, sorry guys if it takes too long. So now it emits fluids. That particles spawning particles that emit other particles, which is fluid that goes with the gravity to the floor. Doesn't get more awesome than this. And that's pretty much everything, guys. I will do a couple of more commits today, so check out the Genome2D sources and you can play with that. And thank you for watching. And if there are any feedback, anything, just shoot me a line, and I'm glad for any suggestions, any bug reports, pretty much anything. Thanks, guys.